Welcome back to Calculus 2 practice problems, where we're looking at alternating series and whether they converge or diverge. So for the most part, alternating series are actually pretty simple. In alternating series, we have a series, an a sub n, and part of that a sub n, in this case I left it out, is an alternating term, which will just continue to alternate between 1 and negative 1, right? Because for even powers, so in this case, for even powers of n, we will have a positive 1. And for odd powers of n, we'll have a negative 1. And it's the opposite for this one, right? Odd powers of n will produce an even exponent and therefore a positive 1. And even powers of n will produce an odd exponent, so we will continue to have the negative 1. So it's just, instead of a series doing something like this, in this case now with this alternating term, it's just going to go above and below the x-axis, but it still might converge. So let's look at this case. They converge, there's only two rules. They converge if the limit as n approaches infinity of a sub n equals 0, and if the term after a general term is less than it, which basically just means is it decreasing, is a sub 4 less than a sub 3. That means is the term after 3 less than it. Just a fancy way of saying that it's decreasing, but that's probably how your textbook will say it. Here's the good news. We already do this. We already check and see if the limit as n approaches infinity of a sub n is 0, right? That should be our first move in every series divergence test. For example, this series, missing my n, this series, we should always check the divergence or convergence of it with a limit test. Limit as n approaches infinity of a sub n. Really, this is all a sub n in this case, but, well, we can leave it out. Because it's just bounded. It doesn't really affect the convergence or divergence. So we'll call this a sub n. The limit as n approaches infinity of e to the negative n. Let's rewrite that as 1 over e to the n. You can see when you plug in infinity, you're just going to get 0. Oh no, the divergence test is inconclusive, right? But isn't that just the first step? We want the limit to be 0 for the alternating series test. So just because it equals 0, we can see that because it's alternating, we have satisfied the first condition. The second condition is that it must be decreasing. So is e to the negative n, decreasing? Well, I think so. As n increases, the denominator increases. When the denominator increases, we can see that the entire fraction will, the denominator increases, which means that the entire fraction will decrease. So we could say that the next term will be less. 1 over e to the n will be less or greater than 1 over e to the n plus 1. Okay, so the two conditions are satisfied, right? There's 1, there's 2 that is decreasing. Another way would be to plug this into your calculator, your graphing calculator, and see, does it have a negative slope? Does it do something like this for the graph? So because these two things are met, we can say that it will converges. That's all. That's why alternating series test is pretty useful. It's just pretty rare that we'll see this, and like maybe 1 or 2 questions on your test will have it, but we don't really see it in general. That's why it's pretty simple. But let's look at another one. What about this? So let's call this a sub n again. And let's take, first of all, let's do the divergence test. Limit as n approaches infinity of a sub n over 3 to the n plus 2, right? This n is kind of going to cancel what this n does. That 2 doesn't matter, so we get 1/3. Oh, wait a second. 1/3 is not equal to 0, so we don't even have to do the divergence test. We could just say it or we don't even have to do the alternating series test. We could just say it diverges by the divergence test, right? Because the limit is not 0. Remember, that was the condition in the first series video, is that the limit as n approaches infinity of our sequence must equal 0. Since it doesn't equal 0, divergence by the divergence test. Okay, let's look at another one. How about this one? The limit as n approaches infinity of a sub n is equal to 0. Check. Is 1 over n decreasing? Yes, it's always greater than the next term. Right, because 1/3 is greater than 1/4, which is greater than 1/5. It's decreasing. So it converges by AST, the alternating series test. Hang on though. Don't we know something? Don't we know something about this series? We know that this diverges. We know that this series right here diverges. It's a divergent harmonic. So how can, just because it alternates, it becomes convergent? Divergent harmonic. So this is a special case here, where if we were to essentially take the absolute value of this a sub n, basically if we got rid of the alternating term, and that remaining a sub n is said to diverge, we can't just say that it's convergent, because it's not. What we can call it is conditionally convergent. So that's another thing that makes this section a little bit tricky, but it's not too bad. So for the remainder of the problems, if after you find that it converges, so we say it's conditionally convergent, after you find that your alternating series converges using the AST, you also want to check what it does without the alternating term. In this case, because without the alternating term, it diverges, we can't say that it is absolutely convergent. That would be in the past videos, we've looked at absolute convergence. So now, with the alternating series test, we have conditionally convergent. In these cases, or this case, e to the negative n by itself would converge. So this would be a conditionally, or no, not conditionally. Since it already converges without the alternating term, we can say that it is absolutely converges, absolute convergence. Otherwise, it will be conditional convergence. So we'll look at a few more examples. How about this one? The limit as n approaches infinity of 1 over n squared is equal to 0. Check. And 1 over n squared is definitely decreasing. Right? Think about 1 over 4 being greater than 1 over 9, being greater than 1 over 16. It's definitely decreasing as n increases. Okay, so it's decreasing. So we can say that it is convergent by AST. But hang on, now that we've reached this point, we have to also check what would it do without the alternating term. What would this series do? This is just a convergent P series, right? P is equal to 2, which is greater than 1. So it's a convergent series. So because without the alternating term, it is convergent, and it is convergent with the alternating term, we will call this absolute convergence. So it's absolutely convergent, right? Maybe let's look at another case of conditional convergence. Let's see. Let's see if this is conditionally convergent, absolute convergent, or divergent. We'll take a limit as n approaches infinity of 1 over n plus 4. We're going to get 0. The first condition is met. Is it decreasing? Is 1 over n plus 4 equal or greater than 1 over n plus 5, the next term? I'd say so, because once again, the denominator is increasing a lot slower than the last case, slower in this case than the last case, but the denominator still is increasing as the terms move on, which means the entire fraction is decreasing. So both conditions are met. It is convergent by the AST. But we got to check if it's conditionally convergent or absolutely convergent by looking at the series without the convergent term, the alternating term. So what we do, we get this. This is why we had to, you might have thought before this that maybe we could have learned this one, maybe even in the third video, right after the infinite series video, because it's fairly easy. But no, because how would you, when you're checking for conditional convergence is how it gets a lot of people, because how would you prove if this series right here was convergent or divergent? You need the skills that we learned in the last video with the comparison tests. Those are very powerful. What we could do is compare this to this series. We could compare it to 1 over the square root of n, right? In other words, 1 over n to the 1/2. We can just drop that 4 because they're very similar without it, right? Well, actually what we could do is, there's an issue here, right? I'm seeing there's an issue here. We can't plug in 0 into that square root of n because, or you know what, we don't even have to do a comparison test. So maybe you could have done this right after that third video. What we could do is adjust the series to start at 4 instead. We did this in the geometric series video. If we start the series at 4 instead, let's see, what would be the first term, second term, third term? If we're starting at 0, we would have 1/2, 1 over root 5, and then 1 over root 7, right? If we started at 4, we can instead just do this, right? Because 1, 2, 3, when you plug in 4, you get 1/2. When you plug in 5, you get 1 over root 5. Finally, when you plug in 3, when you plug in 2, you get 1 over root 5. When you plug in 3, you get 1 over, or I'm sorry, not plug in 3. I had it right the first time. The second term is when you plug in 5 and you get 1 over root 5. The third term is when you plug in 6. So this would not be 7. This would be 6. And the third term in this one would be when you plug in 6. So you can see that these two series are equal to each other. But by starting at 4, we can see that this one is a divergent p-series, right? This is 1 over n to the 1/2. It is a divergent p-series, where p is equal to 1/2, which is less than 1. So it is a divergent p-series. So in this case, I decided to not do a comparison test. Instead, because this would be a lot easier to rewrite it starting at a different term, so we're able to get rid of that 4. So starting at 4 instead, we can see that this is a divergent p-series. So in essence, without this alternating term, without this term right here, this alternating term, this series will diverge. And with the alternating term, we prove that it converges. So what do we call that? We call that conditional. Conditionally. Spell that right? Conditionally convergent. So we have looked at cases of absolute convergence, like the first one, divergence, just if these two conditions are not met, right? But we already know that that would happen with, what is it? We already know that that would happen if the limit as n approaches infinity does not equal 0. So if this condition is not met, if this condition is not met, we already know that it's divergent because of the divergence test. So the alternating series test is pretty cool for all of these kind of series that alternate. That's how you prove converge or divergence of these alternating series.